Here we have a rather tricky standard deviation problem-solving problem, which requires you to investigate and use the formulas, or one of the formulas, for standard deviation. Now those formulas are given on the formula sheets. So which one to use? Well, actually it doesn't matter, but I tell my students that of the two formulas which are here, you should never need this one. Now, as it happens in this question, it's slightly more efficient to use this one, but the other one still works. So it still remains the case that this one is not actually necessary. When you're dealing with actual data and manually calculating standard deviations, then you definitely shouldn't use this one. This is way more efficient. And in this case, I'm actually going to show you how you can solve this question using both formulas. So method one, using the normal formula, the one that we prefer. Well, let's first write down what we know. We know that the standard deviation is root 6, and using what we know about the various variables, we know that n is 24 because it's 24 students, and the mean, we're told, was m. So x bar is m. So we have this odd-looking formula. We don't know what the sum of the squares of the original data were, but that's okay, because if we rearrange this formula, we can very easily work out just rearrange to get sigma x squared on its own. So we've now got an expression for sigma x squared. And remember, sigma x squared is the sum of the squares of the original 24 pieces of data. Now, when we've got 26 pieces of data, let's first think about what the new mean will be. If the mean of the 24 pieces of data was m, and then we've brought along m minus 4 and m plus 4, how's that going to affect the mean? Well, you can set up equations and check, but it's not going to affect the mean at all. This problem's been set up so that it doesn't change the mean. You'll still have mean m, but it'll be over 26 pieces of data instead of 24. So we're trying to find, I've called it sigma 26, just to remind myself it's not the same sigma as before. So sigma for the 26 pieces of data, using the same formula, we've got sigma x squared, but remember, sigma x squared, and this one here, means the sum of the squares of the original 24 pieces of data. So if we're using a standard deviation formula for 26 pieces of data, we need to add the squares of the new pieces of data on. And the new pieces of data are these. So if we add those squares on, that's our new sigma x squared, if you like. Divided by 26, and then we need to take away the new mean squared, but we've already decided that the new mean is also just m. So we can now use the sigma x squared from before and substitute it in here. Now I've not left myself very much space here, but so that was sigma x squared was 144 plus 24m squared. And then continuing that numerator, but I'm going to expand these two expressions. We get plus m squared plus 8m plus 16, plus m squared minus 8m plus 16. Now, because I've run out of space, I'm just going to simplify that, which gives us 176 plus 26m squared, and that's divided by the 26, take away the m squared. And if you continue to simplify that whole expression now, you realise that you've got 176 over 26, plus, look, this divides by 26 just to give you m squared. When we take away m squared, we lose the m altogether. And of course we expected to lose the m altogether because we're told that we can find an exact value for the standard deviation. So we just get that value there, which is roughly 2.6. So now here's a slightly more efficient way of solving this problem, which is to use this formula here. So I'm calling this method 2. Well, first we need to just acknowledge, what is this numerator telling us? What does this mean? Well, it's the sum of each value in the original data, take away the mean, and then we square that. In other words, if you take the value and take away the mean, and then square it, you've basically got the distance between the value and the mean, but squared. So we could say that that expression there means the square of the distance of value x from the mean. So if you think about how far each piece of data is from the mean and square it, and then add all those up for all the different pieces of data, that's what that numerator means here. Now, notice up here I've written both of these are distance 4 from the mean, because remember, using this method is all about how far is each piece of data from the mean, and both of these are 4 away from the mean. Great. That allows us to, well, if we first do this thing a little bit like before, first we had to use the square root of 6 here and set up this equation here. We're going to do that again here, so the original standard deviation equals that numerator divided by 24, and get rid of the square roots, and times by 24 on both sides to get that funny expression in the numerator is just equal to 144. Now when we've got the 26 pieces of data, we've got that funny expression, which is the sum of the squares of the distance from the mean for all of the 24 original data, plus the squares of the distances from the mean of the new pieces of data, all divided by 26. And if we substitute our 144 in for the sum here, we just straight away get 176 over 26, which is the same value as before. I would consider that to be a pretty hard question. That particular question we know isn't going to come up because it was in one of the practice papers. But a question like it might, and there are a couple of questions a little bit like this one in the Cambridge University Press Book 1, the Red Book 1, the Year 1 book. So if you look at the standard deviation chapter there and just look at the exercise there, you'll see there's a couple of questions just like this, so it might be a good idea to have a crack at those.